All right, hello everyone. This is Dr. Gallenstein, and we are about to embark on lecture number 2. So in lecture number 2, we are going to continue our review of statistics, and particularly we are going to emphasize the topic of what we call statistical significance. Really what we're doing here is we want to find out whether something that we observe in our data is the result of a real variation in our data and not just something that is there by chance. We want to be able to tell, okay, if I have some difference in my data, is that difference in my sample data because there's a real difference in the population? Or is it just by chance that my sample has this particular difference? Okay, and so if we have reason to think that what we observe in our data is not by chance, but instead it's a reflection of reality, of something true about the population, then we say that it has statistical significance. All right, that's what we're going to look at today. Now, the way that we're going to do this is we're going to review a couple of concepts first. We're going to build kind of the foundation. We're going to look at a measure of relative standing called a Z-score, or you will later call it a Z-statistic. Then we're going to review the sampling distribution of the mean, because that will be a very important concept for this. Third, we're going to look at hypothesis testing. And then finally, we're going to do a kind of a demo or a practice in Stata where I've given us some questions that we might want to answer, and then we're going to look into Stata at how we might want to answer them. All right, so let's begin. Measures of relative standing. All right, now to begin this section, I want to do a short review on what a standard deviation is. In the last lecture, we mentioned, okay, the standard deviation is the square root of the variance, and it is some measurement of the amount of variation that you have in your data set. Okay, I want to make that a little bit more clear, and then I want to show why that's such a valuable measurement. Okay, so what you see in front of you is a distribution. Okay, it communicates to you the probability of observing particular values of a random variable. Okay, so we know that values that are up here around 0 is right here, the mean, the average. In this particular distribution, the values around 0 are much more likely, whereas the values around -4 or the values around 4 are much less likely. Okay, that's what this distribution communicates to us. It tells us how the values of this random variable are distributed. Okay, and we're looking in this case at a standard normal distribution. I'll talk about that more in a minute, exactly what that is. But now, a distribution has a bunch of characteristics like a mean and a variance and a standard deviation. Standard deviation is going to be a measurement that will communicate to you how widely dispersed the data is. So let's just drive that point home. Here's an image of 3 different distributions. And they all have the same mean, they all have the same average of 0, but they have different standard deviations. Standard deviation, the one with the smallest standard deviation is this red line, so a standard deviation of 0.4. And you'll see that it's a much tighter distribution. A lot more of the values are around the mean, around 0. A lot less values are out in what we call the tails. That means out here on either end. Okay, that means it's much more likely to get a value around 0, around the mean, and much less likely to get a value out in the tails. But now contrast that to a distribution that has a larger standard deviation. So let's look at the blue line. If you look at the blue line, this has a standard deviation of 1. Same mean. That means it is most likely that you'll get a value somewhere around 0, somewhere around the average, somewhere around the mean. But because its standard deviation is higher, there's more variation in the data set, or in the data point, or in the random variable. That means it's more likely for you to find a value that's out in the tail. We can see the blue line is above the red line, so it's more likely to get a value out here around 1 or 2 or 3 than it is with the first distribution, the red one. But it's less likely for you to find a value near the mean for the blue distribution than it is for the red. So I hope that you can see from this that a bigger standard deviation means a more widely dispersed distribution. All right. So let's keep going. Now I mentioned a moment ago, here's our same distribution here. We call this a standard normal. A normal distribution is a distribution that looks like this. It looks like a bell. Sometimes we call it a bell curve. It's a distribution that is centered at the mean. The most likely values are close to the mean. And it is symmetrical on either side. A normal distribution is characterized by two parameters, its mean and its standard deviation. What we're looking at here is called a standard normal distribution. A standard normal distribution. A standard normal has a mean of 0 and a standard deviation of 1. So you can see the mean for this distribution is 0, and we can see the standard deviation is 1. Okay, so let's try to drive this point of the standard deviation. Let's drive this home a little bit. What we can do, and what's so valuable for us, is that we can say that we can measure any particular value of the random variable in terms of standard deviations away from the mean. How many standard deviations is any particular value away from the mean? All right, the standard deviation becomes a really useful unit of measurement. Okay, so let's take a look here. Our mean is 0. All right, our mean is 0. Now let's say that I picked a value of 1. So this is a random variable. It can take any value from negative infinity to infinity. And I go out and I collect a single data point and I get a value of 1. I can measure this value of 1 in the number of standard deviations it is away from the mean. On a standard normal distribution, the standard deviation is 1. That means 1, the value of 1 is 1 standard deviation above the mean. Same here. 2, the number 2 is 2 standard deviations above the mean. And again, 3, the number 3 is 3 standard deviations above the mean. If I drew a number of 2.5, that would be 2.5 standard deviations above the mean. If I drew a number of negative 1, that would be 1 standard deviation below the mean. If I drew a number of 4.5, that would be, of negative 4.5, that would be 4.5 standard deviations below the mean. Okay, so standard deviations become a useful unit of measurement. What we can do is we can communicate how far away a particular value is away from the mean in the units of the standard deviation. That's going to be very important. Okay, I want to pause here for a second and go into Stata. We're going to use the data set we used from the first lecture. It's a data set that collects records on hourly wages, education, and experience for 526 individuals. And we're going to go into Stata and we're going to produce an observed distribution for wages, some descriptive statistics for wages, and then we can use that to discuss what we were just looking at. That is the standard deviation. All right, so let's pull up Stata. I'm going to pull up a fresh window for Stata here. All right, so we're just going to do this quickly. All right, here we go. We got our main window. This is what I always do, and I highly recommend it. I put the output window on one side, okay, and then I like to have my do file, all right, my do file on the other side. Highly recommend you set your screen up this way. You don't have to. It's your preference. I really like it this way because I can have one do file and I can work in it, and I can always see my results over here. Okay, now I want to import my data. So let's import my data. I'm using wages 2. Very similar data set to the wages data I used in the last lecture. Let's open that up. We got wage, education, experience, non-white, female, married, and I added this one since last time. It's called job. It's what sector the job that you're in is. Okay, so let's take a look at this. What do we want to do? What are we doing here? All right, let's make a note of this. generate an observed distribution. All right, generate an observed distribution. Let's do that. Okay, density wage. All right, so we're going to do that first. We're going to generate that observed distribution of the wage variable. There it is. All right. It's not a normal distribution. You can tell it's not normally distributed because there's a lot of values out here and there's very few over here, and so it's not symmetric, but it has some similar characteristics. All right, so there's our distribution. Now let's get some summary statistics on this. All right, whoops, sum wage. All right, summarize wage. Let's click that. Boom. All right, here we go. What do we got? We've got a mean of 5.9 and a standard deviation of 3.7. Now that we've got that, let's go back to the lecture, and I'm going to illustrate the same topic using our sample data. All right, so here we are. We're back. Let's take a look. So there's our observed distribution of wages that we just generated. I already had in here. Now our mean is 5.9. Okay, we just observed that from our summary statistic. Well, let's think here. As I just said, I can measure values as the number of standard deviations that they are away from the mean. Well, our standard deviation is 3.7. That means if I wanted to go one standard deviation above the mean, I would go to 9.6. 9.6 is one standard deviation above the mean. And then let's go 2. 13.3 is 2 standard deviations above the mean. Okay, so we can measure any particular value in terms of the number of standard deviations that they are away from the mean. This, like I said, is going to be very useful. All right, but now let's keep driving this standard deviation point home. All right, we mentioned before normal distribution looks like a bell, so we call it a bell curve. And what we're looking at here is we're looking at a normal distribution. And there's some neat properties of a normal distribution when we think about the standard deviation. So what we have here is we have our mean value, the average value. And then what we've noted on either side here is the number of standard deviations away from the mean. This is one standard deviation above the mean. This is one standard deviation below the mean. This is 2 standard deviations above the mean. And this is 2 standard deviations below the mean. All right, and so on. And what you can see from a normal distribution is that there is a certain amount of data that falls between the mean and one standard deviation away from the mean. So in a standard normal distribution, 34.1% of all the data in your sample, or all the data in this random variable, 34.1% of the data fall between the mean and one standard deviation above the mean. Another 34.1% of the data falls between the mean and one standard deviation below the mean. So basically, the standard deviation can help us to know how much data is, or how, what proportion of our population falls within a particular range. Basically, we can look at this and we can see, okay, in the space between -1 standard deviation and +1 standard deviation, around 68% of the data, 68% of your data falls between -1 and +1 standard deviation. 95% of the data falls between -2 and 2. 99% of the data falls between -3 and +3 standard deviations. That's an important point. 99% of the data, 99% of your data value will fall between -3 standard deviations and +3 standard deviations. That means it is extremely unlikely to observe a value that is more than 3 standard deviations above or below your mean. Very, very unlikely. Now, this is going to be an important concept. What we're going to be thinking about today in this lecture is how likely or unlikely a particular value is, how extreme a particular value is. And so what we can see here is that, values that are between the mean and one standard deviation are very likely. A lot of the data is in this range. 68% of the data is between -1 and 1 standard deviation. And as we go farther out, a lot less data is out here in these tails. It becomes very unlikely to observe something that is more than 3 standard deviations above the mean. All right, that's a very important concept. So what we want to do here, I've been alluding to this. I've been saying, okay, hey, let's go back here. I've been alluding to the fact that any particular value can be measured in terms of the number of standard deviations that they are above the mean. Well, let's make that more concrete. This measurement is called a Z-score. It is the number of standard deviations that a given individual data value is away from the mean. And here are the equations. We can have a population Z-score, or we can have a sample Z-score. What this is, again, this is a measurement. It's a measurement of how far away a particular value is from the mean, measured in units of standard deviations. Okay, so let's take a look at how it's calculated. What it is let's focus here on the sample, because that's what we're always working with. Let's look at the sample. So this is our particular value minus the mean, divided by the standard deviation. So that gives us a measurement, a standard measurement of how far away our particular value is from the mean in units of standard deviations. And so what we can do with this, okay, this value, this Z-score, all right, is what we call a Z-score. This Z-score, we'll take a value of 0 if you're on the mean. If your sample value is actually the mean value, then your Z-score will be 0. And then it increases and it decreases off in both directions. It increases and decreases off in both directions. And it's telling you, it's communicating to you how many standard deviations you are above or below the mean. And so, as we were saying before, okay, it's really likely to have a value between -1 and 1 standard deviation. And it's fairly likely between -2 and and -9. Actually, it's really likely to get a value between -2 and -3. I'm sorry, -2 and +2. It's almost certain that you will get a value between -3 and 3. And so if you end up with a value that's out here, it's extremely unlikely. That means it's an outlier. It's very unlikely to find that. Okay, so let's think about this another way. If our Z-score, let's say our Z-score is between -1 and 1. That means that particular value point, that particular data point, is a highly likely data point. It's a very entirely ordinary value. Even if we go out to maybe 2, we're looking at ordinary values in our data set. But now, once we get out between 2 and 3, that means between 2 and 3 standard deviations away from the mean, that would be out here into this 2 to 3 standard deviations away from the mean. We start to get there's a pretty low probability of finding a value that's in this range. In this graph, we say 2.1% probability of being between 2 and 3 standard deviations, and a 2.1% chance of being between -2 and -3 standard deviations. So we're looking at unusual values. It's unlikely to get a value between 2 and 3 or between -2 and -3. And then if you find a value that is larger than 3 or less than -3, we're talking about a very unlikely value. If your Z-score is above 3 or less than -3, this is an extremely unlikely value. This is called an outlier. Okay, so this Z-score communicates to us how extreme a value is. Is it really likely or is it really unlikely? And it does it in units of standard deviations. Okay, so that's laying one important killer foundation in this lecture is a measure of relative standing. How extreme is a value? Now, the next pillar that we need to build, that we need to put in place, is a sampling distribution of the mean. We talked about this in the last lecture, but I'm going to talk about it again because it's an important concept, and I think it's kind of challenging to kind of understand what this is. So I'm going to review it. All right. So here's the point. Every time that you take a sample of data from the population, you will find a new sampling mean. Whatever variable it is, let's say, actually I'm going to use an example of land size, so let's say that now. You go and you collect a sample of data from farmers, and you want to know how much land they have. Every time you go and collect a different sample from the population of all farmers in northern Ghana, every time you go and collect a subsample of those farmers, you'll find a new sample mean. A new sample mean land size. And because of this, we can see that this sample mean is itself a variable. It's a variable. The first time you collect a sample, you'll get one value. The next time you collect a sample, you'll get another value. The next time you collect a sample, you'll get another value. It's a variable. It's a mathematical expression that can take different values based on a distribution. And so this sample mean has its own distribution. It's not the same distribution as the distribution of land size in your data set. This is the distribution of the sample means. We call it the sampling distribution of the mean. That's the probability distribution of all the possible sample means. It tells you how likely it is of observing a particular sample mean given your population. All right, let's try to make this more concrete. So we're saying sample means, okay, and it has a distribution. But now let's do the same example from the last lecture. We're just going to reinforce it here because I think this can be very confusing. Let's say all these orange farmers, these are my farmers. They're orange and they've got a little farming tool here. So all of our farmers, this is our population. When we go and collect data, we don't collect data on every single farmer. We collect the data on some subset. All right? But there exists a true value. That means a true value for the population. So let's use our example of farm size. That population, all of the orange farmers, that population has an average farm size of 15 acres. I don't know this population mean because I can't collect data on all of them. But I will go in, I'll collect data on some of them, some subset. So let's say it's the blue ones, the blue farmers, all right? I'm collecting data on these blue farmers. It's some subset of all the farmers. And I calculate the mean of my sample data. So the mean of the blue farmers. And I get 14 acres. Well, that is one observation of the random variable, the sample mean. It's one observation, but we can get another. Let's do another sample, the green farmers. We get a sample mean of 18. We go in, we collect data again. This time, the red farmers, all right? And we get a sample mean of 15.5. And we could keep going. We keep going and collecting different samples, and every time we collect different samples, we'll get a different sample mean. So the sample mean is a random variable. Every time we go and collect a sample, we get a different one. That means the sample mean has a distribution. So here we're laying it out, the sampling distribution of the mean. You'll notice that this distribution is shaped like a normal distribution. That's because it's a normal distribution. The sampling distribution of the mean is, it approximates or it approaches a normal distribution as your sample size gets larger. Okay, the sampling distribution of the mean. The sampling distribution of the sample means. It's a distribution that communicates to us the probability of finding a particular sample means when we collect samples of data. The sampling distribution of the mean has a mean. That means there's some average value of all the possible sample means. And the average value of sample means is actually the true sample, the true population mean of 15 acres. All right, so every time I go and collect a sample, so it's the first time I did it, I did the blue farmers, and we found that the sample mean land size for the blue sample was 14. So here's that sampling. There's that sample mean. And then I go and I collected another sample mean. This time it was the green farmers, and it was 18 acres of land. And the next time I collected a sample from the red farmers, and it was 15.5. What you can see is that every time I go and collect a sample, it is some particular value from the distribution of sample means. And I could keep going and keep going and keep going. The most likely sample means that I will get will be the ones that are near the mean. I'm most likely to find sample means that are in this area, somewhere around the mean, somewhere around 15. Those are most likely. You can see it from the distribution. It's very unlikely to find a sample mean that's way out here near 25 or way down here near 5. Very unlikely. Okay, so this is the sampling distribution of the mean. Now we're going to want to know how extreme values are. So extreme sample means. So let's think about this. Imagine that we went in and we collected a sample of data. Let's use our standard. We're collecting a sample of data from farmers in northern Ghana. And we go in, we collect one sample of data, and we find that our sample mean, that means the average land size in our sample, is 19 acres. All right, we only have one sample. We don't have the population. We don't have a whole bunch of samples. And so once we've observed this 19 acres, we don't actually know how good, we don't know how close that is to the true population sample, the true population land size. We don't know. Now, of course, in the example, given that I'm using the same example, I've already told you what the population is. All right, it's 15. But in real life, when we go and collect data, we don't know what the true population land size or whatever is. We don't know what the true land size is. All we know is our sample mean. And so it would be pretty important for us to know whether or not our sample mean is likely to occur or unlikely. We want to know how extreme it is. We want to get a measure of how far away it is from the mean. But we don't have the true sampling distribution of the mean. We don't know it. We've only collected one sample. We want to know if our sample mean is an outlier. Okay? Well, we can use our z-statistic. We can use our z-score to kind of get an idea for how extreme a particular value is. Okay, we might want to know how extreme our sample mean is. All right, so this is how we do it. So we use the z-score, all right, the number of standard deviations that a given individual data value is away from the mean. We want to use a z-score to know how far away our sample mean is from the mean of the sampling distribution of the mean. We want to know how far away our particular value is from the mean of the sampling distribution of the mean. Okay, so that's what we want to know. So as our z-score, what our z-score would be is that we have a particular value of our sample mean minus the true population mean divided by the standard error. And remember, the standard error is the standard deviation of the sample mean. We calculate it. So we want to know, so the standard deviation of the sampling distribution of the mean is the standard error. And the way we calculate it or estimate it is it's the standard deviation of our sample data divided by the square root of our sample size. That'll give us the standard error of the mean, which is the standard deviation of the sampling distribution of the mean. Okay, now you might notice that actually we have a problem here. Like I said before, we don't know the true population mean. So unfortunately, we can't directly measure we can't directly say how extreme our value is our particular sample mean value is, we can't say how extreme it is relative to the true sampling distribution of the mean. We'd love to know it. We can't know it because we can't know this true mean. But right now, we are building the foundation for our hypothesis test. So we can use this Z-score, or what we'll see in a moment called a T-score, to find out meaningful things about our observed value. Okay, so we're going to make this more clear. Just a minute. All right. Now, if our sample size is sufficiently large, we will use a Z-statistic. However, usually we use what's called a T-statistic, which is pretty much the same thing as a Z-statistic, except the distribution is a little bit different. It's when our sample size is not large enough, we'll use what's called a T-statistic. I'll make that more clear later in the lecture. Okay, but a T-statistic tells us, or a T-score or a T-statistic will tell us how extreme a particular observed data value is. The larger your T-score is, the less likely it is for you to observe that data point given your distribution. Okay, now that is the foundation. We've reviewed standard deviation. We've figured out that we can measure how extreme a value is in units of standard deviations using a Z-score or a T-score. We've reviewed the sample distribution of the mean, which is the distribution of the sample means in our data set. It's the distribution of sample means, we'd say, from our population. Okay, and we can calculate the standard deviation of the sampling distribution of the mean by calculating the standard error. All right, with all of those tools, now we're going to be able to do something called hypothesis testing, where we're going to use all of these things to really determine how extreme values are, and use that. We're going to use that to test hypotheses about our data. Okay, so then let's go. Let's do it. Let's do some hypothesis testing. This is critical. It's central for econometrics. We do hypothesis testing all the time. All right, so we need to make sure we get this. All right, what is hypothesis testing? Hypothesis testing is basically using statistics to perform the scientific method. In the scientific method, we have some observation, we have some question, and we formulate a hypothesis about what we think is true. And then we conduct an experiment to evaluate that hypothesis. All right. So what we're doing in statistics when we do hypothesis testing is that we are stating a claim about the population. Remember from the first lecture, we're always interested. We want to know what is true about the population. And we use sample data to figure out or to estimate what's true about that population. And so that's the same thing we're doing here. We are stating a hypothesis about what is true about a population. And then we are analyzing our sample data to determine or to provide evidence for whether or not that hypothesis about the population is true. We are interested in knowing whether or not any variation in our data set is a result of just mere chance, or is it a result of the fact that there is really a true phenomenon in the population. All right, let's make this more clear. All right, first let's begin to kind of build our framework here, and then we're going to use an example that I think will drive this home. Okay, so a hypothesis is a claim or a statement about a property of a population. So using our standard example, a hypothesis could be fertilizer increases farmers' yields. I'm making a statement, a claim about something in the population. I'm saying that in the population of farmers, that fertilizer increases their yields. I'm making a statement or a claim about something that is true in the population. A hypothesis test is a procedure for testing that claim about a property of the population. What we do in statistics is we always propose two hypotheses, and then we'll test. We always propose what's called a null hypothesis and an alternative hypothesis. A null hypothesis is a statement that the value of some population parameter, let's say it could be income, land size, etc., has some particular value. We're always assuming in the null hypothesis that that there's no if we're measuring the effect of something, we always assume there's no effect. If we're interested in whether or not a data value is greater than 0, then the null hypothesis is always that it's 0. The null is always that whatever we think might be true, the null hypothesis is always that it's not true. Okay, I'll make that more clear in a minute. The alternative hypothesis is a statement that the parameter has a value that somehow differs from the null hypothesis. Maybe it simply just does not equal 0, or maybe it's greater than 0 or less than 0. Usually the alternative hypothesis that's the one that we think. That's the one that we're kind of testing. Like if I said I'm asking the question, I'm making the claim, fertilizer increases farmers' yields. My null hypothesis would be fertilizer does not increase farmers' yields. And my alternative hypothesis would be fertilizer increases farmers' yields. Okay? And then what we're going to do is we're going to see whether we can accept or whether we can reject or fail to reject the null hypothesis. We'll see that in a minute. But now let's give an example and let's make sure that we have our intuition clear before we go into actually performing the hypothesis test. So, using our example, do farmers that use fertilizer have higher incomes? Now imagine that we go to a village in rural DRC. And in this particular village, farmers have never used fertilizer. Okay, that may or may not exist. I'm sure that farmers in DRC, even really rural DRC, have used fertilizer. But let's just assume this, all right? We run a development program that provides a random sample of farmers with fertilizer. The average income of farmers that did not receive the fertilizer is $600. Now we want to know if the fertilizer increased their incomes. We state a null hypothesis that fertilizer had no effect. That is, the average income for farmers with fertilizer is $600. All right, so our null hypothesis is that fertilizer has no effect. Our null hypothesis is that fertilizer had no effect. All right, so what we do is we say, all right, the average income for farmers with fertilizer is equal to 600. That's our null hypothesis. If the average income for farmers with fertilizer is 600, that would imply that fertilizer had no effect. All right. We also state an alternative hypothesis. That is, average yield for farmers, or average income with farmers, for farmers with fertilizer, is greater than 600. So here's our alternative hypothesis. This is the one that we think is true. We think, by our intuition, that fertilizer will increase incomes. So we state the null hypothesis, basically that it has no effect, and then we state the alternative hypothesis, and that is that it does have an effect, it increases. Okay, so that's to make it more tangible. But now let's make sure we get the intuition down. Let's make sure we get the intuition clear. Basically what we have here is that we're collecting data among all the farmers that use fertilizer, and we're going to observe a particular sample mean income for farmers with fertilizer. Okay, now if you remember before, if we wanted to calculate a z-statistic, we would take the value, the observed sample mean minus the population mean divided by the standard error, and that would give us a z-score, or a z-statistic, or a t-statistic, which would allow us to see how extreme our value is. Okay, but we don't know the true population. Remember, I said before that we don't know the true population mean, and so we couldn't calculate our z-score. Well, here, now, in this example, we're going to be able to see why the z-score, the t-score, is really useful for us. Because what we're going to do is we're going to assume that either the null hypothesis is true or the alternative hypothesis is true. And we're going to assume that they both have a particular distribution with a particular mean. Now, I don't know the true sampling the mean of the sampling distribution of the mean, but I can look at distributions of the sample mean as if the hypotheses were true. So let's look at that. So here I have a sampling distribution of the mean. If this is what the sampling distribution of the mean would be if the null hypothesis was true. Now, I don't know if this is the true sampling distribution of the mean or not. I don't know. But this is what it would be if the null hypothesis were true. So if we assume that the mean is 600, then we can create a z-statistic. We couldn't before because we didn't know what the mean was, the population mean was, the mean of the sampling distribution of the mean, the sampling distribution of the sample mean. But what we're going to do in a hypothesis test is assume one. We're going to assume one based on our null hypothesis. This is the sampling distribution of the mean if fertilizer has no effect. We also could state one for if the alternative hypothesis is true, and that is that the mean is some number larger than 600. So this is what the sampling distribution of the sample mean would be if the alternative hypothesis was true and the true mean is some number greater than 600. Okay, so now we have two possible distributions. We have two possible distributions. We don't know whether either of them are true. But what we can do is we can evaluate whether or not we have evidence to think that the null hypothesis distribution is true or the alternative hypothesis distribution is true. Okay, so let's make that concrete. Let's see if we can make that clear. Now, I've just said you've gone in and you've collected a sample of data from these farmers and you've found a sample mean, some sample mean income of the farmers that have fertilizer. All right. Well, let's see. Let's say that you find a sample mean of 650. That's your sample mean. All right. You find a sample mean of 650. That means there's a difference between the group that has fertilizer and the group doesn't. The group with fertilizer has 650, and the group without fertilizer has 600. You might look at that and say, "Hey, there's a 50 unit difference between these two means." That you might then say, "Wow, okay, good. Fertilizer increases incomes." But let's pause for a second. If the true sampling distribution of the mean is 600, how likely is it that you could just by chance observe 650? There is some chance that when you go and collect data, that you'll observe 650. That doesn't mean that fertilizer had an effect. Yes, there's a difference between 650 and 600. Yes, there's a 50 unit difference. But there is some probability that you will find 650 even if the true population mean is 600. So let's take a look at what that looks like on the graph. So here we go. We've got our sampling distribution of the mean if the null hypothesis is true, and we've got the sampling distribution of the mean if the alternative hypothesis is true. And here's our sample mean, 650. Well, if just looking at these distributions, we would say, well, it's actually pretty likely. It's pretty likely that you would observe a sample mean somewhere around 650 if the null hypothesis is true. In this distribution, values around 650 are very, very likely. Whereas if the alternative hypothesis is true, that is, if this is the true distribution in the population, then 650, a value of 650, would be very unlikely. So values around 650 are very unlikely if the alternative hypothesis is true. That would make you think, well, okay, yeah, yes, they have 50 more, but actually it's highly likely to draw a value of 650 if the true mean is 600. That means I don't have any reason to believe that there is actually a difference. I don't have any reason to believe that my observed 650 implies that there is a real difference between farmers with and without fertilizer. That this 650, that 50 unit difference could just be by chance. It could just be by chance. So we look at this and we say, all right, wow, I got 650. It's pretty likely that the true population mean is 600. It's pretty likely the true population mean is 600, and so I'm going to fail to reject my null hypothesis. I'm going to conclude that it's most likely that the fertilizer had no effect. But alternatively, let's say that we find a value of 900. Let's say our sample mean is 900. Now, if we just look at these distributions, we can say, wow, okay, a value of 900, a value somewhere around 900 is very unlikely if the true population mean is 600. A value of 900 is very unlikely if the true population mean is 600. However, if the true population mean is greater than 600, a value somewhere around 900 is very likely. That would make me start thinking, oh, you know what? I bet that null hypothesis is false. I bet that the true population mean is not 600. So the true population mean for farmers with fertilizer is not 600, but it's some larger number. Because it would be very unlikely for me to get a value of 900 if the true mean is 600, if this is the real distribution. But it would be highly likely to get a number somewhere around 900 if the alternative hypothesis was true, and this was my distribution, the true distribution of the sample means. All right, so this is the intuition behind hypothesis testing. What we want to know is how extreme is our particular observed sample mean if the null hypothesis is true. Because if it's really extreme, then we will reject the idea that the null hypothesis is true. And we would say that we have provided evidence that the alternative hypothesis is true. If our value is really extreme, then we will reject our null hypothesis. We will conclude that our null hypothesis is not correct if we have a really extreme value. And so this brings it together. This is why we need measurements of extreme value. We need to know how extreme our particular value is if the null hypothesis is true. All right, that's hypothesis testing. That's the intuition behind hypothesis testing. Now we're going to make it more rigorous. So let's keep going. All right, first let's clarify some language. So when we test our hypotheses, we draw conclusions about them. The conclusion will always be either reject the null or fail to reject the null. We never accept the null. We never say that the null is true. We never say that the null is false. We only reject or fail to reject. So in our example, the null hypothesis is that fertilizer has no effect on income. And the alternative hypothesis is that fertilizer increases income. Well, when we do a hypothesis, we never say that fertilizer had no impact, or fertilizer did have an impact. What we say is we reject or we fail to reject the null. If we reject the null, that means we have provided evidence that the null is not true. We've provided evidence that fertilizer does have an impact. If we reject the null, that means we've provided evidence that fertilizer has an impact. If we fail to reject the null, that means we have provided evidence that fertilizer does not have an impact. But we never conclude with absolute certainty. And the reason is because there can be error in our hypothesis testing. That means the conclusion that we draw from our data, the conclusion that we draw about our hypotheses could be incorrect. There's some probability that our conclusion about our data could be incorrect. All right, let's keep going. All right, the null and alternative hypothesis make competing claims about reality. Either the null is true or the alternative is true, but not both. So when we use a sample to test hypotheses about a population, we might make an error in our conclusion. We might make an error. Let's take a look at what that looks like. There's two types of error. There's type 1 error and there's type 2 error. Now, a nice way to see this is if we lay it out in the form of a table. So let's take a look at this table. So there's two possibilities. The null is true or the null is false. In reality, either the null is true or the null is false. Using our example, either fertilizer has an impact or it does not. They both can't be true. They both can't be false. They're mutually exclusive. Either the null is true or the null is false. All right, in reality, in truth, in the population. But we don't see whether the null is true or whether the null is false. What we do is we either reject or we fail to reject the null hypothesis. So we can reject or we can fail to reject. If we reject the null, that's saying that we have evidence, or we have reason to believe that the null is false. We have reason to believe that the null is false. We can't say conclusively that it's false, but we have reason to believe that it's false. So if we reject the null hypothesis and the null is in fact false, using our example, if we say fertilizer does not impact incomes and it's actually true that fertilizer does not impact incomes, we would be making a correct judgment. This would not be an error. We would be correct. Likewise, if we fail to reject the null hypothesis, and in fact the null hypothesis is true, again we are correct. So this would be, imagine that we do our analysis and we conclude that fertilizer does not increase incomes. We would fail to reject. We would fail to reject the null. And if, in reality, fertilizer does not increase incomes, we would be correct. We would make a correct decision if we fail to reject the null and, in fact, the null is true. But there's two possibilities of error. Type 1 error is when we reject the null, but the null is true. Rejecting the null means that we have concluded, we believe that we have evidence to suggest that the null is false, and so we reject the null hypothesis. But in fact, the null is true. So this is a type 1 error. There's also the opposite type of error. If we fail to reject the null hypothesis, that means we've provided evidence, we have evidence to suggest that the null hypothesis is true. If we have evidence to suggest the null hypothesis is true, we will fail to reject. But if we fail to reject and it turns out that the null was actually false, that would be a type 2 error. Using our example, let's say in reality fertilizer does not increase yields, but in our analysis of our sample data, we find that yields are significantly larger for fertilizer. That's a type 1 error. We have rejected a true null hypothesis. We've concluded that there is an effect when there is not an effect. We don't want to do this if we're doing research that will influence policy. We don't want to say that there is an effect of something when in fact there is not an effect. If we say that there is an effect when there isn't, then policymakers and NGOs are going to go and invest a bunch of money in something, and all of that money is going to be wasted because there's not an actual effect. So we don't like type 1 error. Let's look at type 2 error. Type 2 error is, in reality, fertilizer increases yields, but in our analysis of our sample data, we find that yields are not significantly larger with fertilizer. In this case, we fail to reject a false null hypothesis. That means that fertilizer really does help farmers, but we concluded that it didn't. This is type 2 error. This is also bad. We don't like this either. We don't want we don't want to discover that, we don't want our research to say that fertilizer or whatever doesn't impact yields, and then no one goes and invests in it because they think it doesn't work, when in reality, it could have worked. So we don't like type 1 error, and we don't like type 2 error. All right. Now, let's get into the nitty-gritty. So we've laid it out. We've laid out the concept that basically what we're doing is we are looking for how extreme our particular sample mean is, how extreme of a value is, if the null hypothesis is true. And if it's really extreme, we will reject the null hypothesis. Let's put that into math, and let's get to it. So we test our hypotheses by constructing a test statistic. A test statistic is a random variable that indicates how far your observed value is from the mean if the null hypothesis is true. So that means we're assuming that the population mean is whatever our null hypothesis is saying that it is. All right, a sufficiently large test statistic will allow you to reject the null hypothesis. To test your hypothesis, we use a t-statistic, just like the z-statistic that we talked about before. We take our particular sample mean value, we subtract the null hypothesis value, and we divide it by the standard error, which is the standard deviation of the sample mean. That's our t-statistic. If we wanted to apply that to our example above, let's use our first example. We said that we collected a sample mean of 650, so we had a sample mean of 650 minus the null hypothesis, where we assumed the null hypothesis was 600. So this would be 650 minus 600, so it'd be 50 on top, and then we divide that by the standard error. All right, that would be our t-statistic. Well, what is a t-statistic and how do we use it? So let's talk about that. All right, now I'm going to hit you with another distribution, and I'm sorry. A t-statistic is another random variable. A t-statistic is a random variable, and therefore it has a distribution. We call it a t-distribution. A t-distribution is very similar to a standard normal distribution, and we use it to test our hypotheses. So here in this graph, I just kind of demonstrate a standard normal distribution is just like the one we saw earlier. A t-distribution has the same mean as a standard normal distribution, but it's a little bit wider. It's more widely dispersed than a standard normal distribution. Basically, our t-statistic is a random variable that is drawn from a t-distribution, which is very, very similar to a standard normal. And what we do is we use how large our t-statistic is measured on a t-distribution to determine how extreme our observed value was. To determine how extreme our observed sample mean is from the hypothesized, the null hypothesis mean. We use this to figure out how extreme it is, and we're using a t-distribution to do it. So let's take a look. Let's make that more clear. T-distribution. You recognize, okay, this is a distribution. It looks very similar to a standard normal, but it's just a little flatter on top and a little more widely distributed. All right. It has a mean of 0. Okay. And what we're going to do, I'm going to illustrate this. I'm going to go through step by step and illustrate using the t-distribution how we do our hypothesis testing. Okay, but just to make this clear, this t-distribution, this is the distribution of possible t-statistics. The distribution of possible t-statistics, it's based on values of our sample mean. All right. All we're doing is, all this is this is kind of normalizing our particular observed value so that we can know how extreme it is and we can test our hypothesis. All right, but we're going to go through it step by step to see how this works, to see how this hypothesis testing works. So first, let's define a couple things. We're going to define critical region, significance level, and p-value. All right, critical region. This is the set of all values of a test statistic that cause us to reject the null hypothesis. All the values of a test statistic that causes us to reject the null hypothesis. Basically, the point is this. This is any t-statistic that falls within the critical range would imply that I reject the null hypothesis. All right. The significance level, that is the probability that the test statistic will fall in the critical region when the null hypothesis is actually true. The significance level is the level of type 1 error. If the test statistic falls in the critical region, we reject the null hypothesis. Okay, I'm going to make all this more clear in a minute, but just got to get our definitions out. The p-value. The p-value is the probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data, assuming that the null hypothesis is true. The null hypothesis is rejected if the p-value is very small. All right. Get the definitions out. I'm going to illustrate it right now. T-distribution. Mean 0. All right. So a critical value. A critical value is some value of a test statistic above which, actually, I think I want this to say critical region. So this line is the critical value, and the area above it is the critical region. All right. So the critical region lies above the critical value. All right. The critical value is some value of the t-statistic above which I will reject my null hypothesis. That means when I calculate my t-statistic, if that t-statistic is above a certain value, I will reject the null, and I will conclude that I have evidence to suggest that the null is false. All right. So this is some particular value. You'll notice it's a certain number of standard deviations away from the mean of the t-distribution. Okay. Now, all the area to the right, underneath the curve and to the right of this critical value, this is the critical region. All this area here is the critical region. All right. This is the critical region. If our t-statistic is in this region, we reject the null. We reject the null hypothesis. All right. The space below the function and above the critical value, so this space, kind of shaded partially here in red, this space is the probability of observing a t-statistic greater than or equal to the critical value. All right. The space underneath the distribution above the critical value is the probability of observing a t-statistic greater than or equal to the critical value. All right. Now, let's keep going. All right. I mentioned before type 1, type 2 errors. Type 1, we get to control how much type 1 error there is in our analysis. We call this the significance level. Okay, let's just use our intuition here. I said that if our t-statistic lies above this critical value, then we reject the null hypothesis. The area, this area, is the probability of observing a t-statistic greater than or equal to our critical value. So this area communicates to us the probability of committing a type 1 error. This is the probability of rejecting the null. This area here is the probability of rejecting the null hypothesis if the null hypothesis is true. All right, if this is the true null hypothesis, if the null hypothesis is true and this is the true distribution, then this area, we've just said that this area is the probability of finding a t-statistic above the critical value. And we've also said that if our t-statistic lies in this area, then we will reject the null. That means that this area gives us the probability of rejecting the null hypothesis when the null hypothesis is actually true. All right, then this is the probability of committing a type 1 error. We get to control how much type 1 error we have by controlling where the critical value is. All right, let's make that more clear. Okay, so we get to control how much type 1 error there is in the analysis. We call this the significance level. The probability of making a type 1 error is known as the level of significance, or we call it alpha. That means the area here above the critical value is alpha. It's the probability. The probability of committing a type 1 error. That is the probability of finding a t-statistic above the critical value if the null hypothesis is true. And we get to decide how much type 1 error we're willing to live with. We can say alpha equals 0.1. That means there's a 10% chance of committing type 1 error. That means a 10% chance of saying that fertilizer does impact yields when actually it does not. Or we can say alpha equals 0.05. That means a 5% chance of type 1 error. Or alpha equals 0.01. There's a 1% chance of type 1 error. We get to decide. And this alpha is going to determine where our critical value is. So let's see it. Our choice of alpha determines the critical value. Alpha is the probability that lies above the critical value, below the curve. Okay, the space below the function, above the critical value or to the right of the critical value, is the probability of observing a t-statistic greater than or equal to the critical value. Okay, this is equal to alpha. This space here is equal to alpha. It's the probability of committing a type 1 error. If we're willing to accept more type 1 error, then we would move the critical value back. And now we would have a larger critical value. With a larger area here. So let's say this is a critical value when alpha equals 0.1. Now there's a lot of space, much more likely to commit a type 1 error. It's much more likely to commit a type 1 error when we use alpha equals 0.1 because there's a 10% chance. This space now represents 10%. There's a 10% chance that my t-statistic will fall in that region. And if it falls in that region, I will reject the null hypothesis. But if the null hypothesis is true, then I would be committing a type 1 error. Okay? We reject the null if our t-statistic falls in this region. So there's a 10% chance of type 1 error. We could also imagine the alternative. Let's say we really don't like type 1 error. We really don't want it. Well, then we set a critical value. We set alpha equals to 0.01. That means 1%. There's a 1% chance that our t-statistic will fall above the critical value. That means it's very unlikely. It's only this little tiny space here. When we set our critical value based on alpha equals 0.01. So there's a 1% chance of type 1 error. There's only a 1% chance that our t-statistic will fall in this region. Okay, so our t-statistic. So if our t-statistic is above the critical value, we reject the null. We reject it at 10% level. All right, so let's demonstrate this. All right, so let's go back to this example. Okay, t-distribution, mean 0. Let's say we base our critical value. We set a critical value based on an alpha equals 0.1. That means there's 10% chance of falling above it. This space here, it represents 10%. Well, when we calculate our t-statistic, we're going to get a particular value of the t-statistic, and we see where it lies. If our t-statistic is out here, that is, our t-statistic lies in this region, then we will reject the null hypothesis. And we will reject it at the 10% level. It lies within that space above the critical value when alpha equals 0.1. So if our t-statistic lies out here, we will reject the null. We will conclude that our particular observed value is too extreme, and therefore we don't think that the null hypothesis is true. We will reject the null hypothesis. But if the null hypothesis is true, we will be committing a type 1 error. All right. And we get to decide how much, where do we want alpha to be? Do we want alpha to be 0.1? Do we want 10%? Do we want a 10% chance of getting a t-statistic in this space? If so, it's much more likely for us to reject our null hypothesis, because it's much more likely to find a t-statistic that's out here. In fact, it's 10%. But let's say we really don't like type 1 error. In this case, there's a 10% chance of type 1 error. Well, let's say we really don't like type 1 error. Let's say we so don't want type 1 error. We never want to conclude that there is an effect when in fact there isn't. And so we say, let alpha equal 0.01. I'm only willing to accept a 1% chance of type 1 error. So let's take a look at that. So here we go. The mean, 0, okay. Now this is our critical value when alpha equals 0.01. So very small chance of rejecting the null hypothesis. Our t-statistic is here again. And now in this case, we fail to reject our null hypothesis because our t-statistic does not lie within the critical range. It does not lie within the critical region. It's not larger. It's not large enough. It's not larger than the critical value. So in this case, we would say we fail to reject when alpha equals 0.01. We fail to reject at the 1% level. Okay. Now, one more point. So when I went through some definitions, I mentioned the critical region. That's this space here. The probability of being in this space is our significance level. So that's alpha, our significance level. Okay. Our t-statistic, we will reject the null if our t-statistic is within that critical region. All right. One last point. I mentioned before I defined this term, the p-value. The p-value is the probability of observing a t-statistic at least as large as the one that you observe. What does that mean? That means the probability of a t-statistic being at or above your t-statistic or our t-statistic. So that's this region here. This region here is the probability of observing a t-statistic at least as large as our t-statistic. All right. So the space below the function and above our t-statistic, or to the right of our t-statistic, is called the p-value. The p-value is the probability of observing a t-stat greater than or equal to our t-stat. All right. So what we will be doing in hypothesis testing is that we will find p-values. And if our p-value is smaller than our chosen alpha, we reject the null hypothesis. So that is, if this green space is smaller than the red space, we will reject the null hypothesis. If our p-value is smaller than our chosen alpha, we will reject the null hypothesis. All right, and now this is what we use all the time is p-values. All the time p-values. We'll see them all the time. And what we want are, small p-values indicate to us a significant result. They indicate that it's very unlikely to observe a t-statistic that we've observed. Okay. A couple of last points. 2 types of hypothesis testing. There are 2 main types of hypothesis testing, and it's called one-tail test or a two-tail test. A one-tail test is when we only look into one tail of the t-distribution, and a two-tail test is where we look into either tail. Basically, what we mean here is, a one-tail test is when our when our alternative hypothesis says that fertilizer increases income, for example. That would be a positive t-test. a positive one-tailed test. A negative one-tailed test would be, let's use an example of like malaria-treated bed nets. We're measuring malaria, and we think that giving malaria-treated bed nets will reduce malaria. So then we would have a negative one-tailed test. A two-tailed test is where we say our alternative hypothesis is it's just that the null hypothesis isn't true. It could be bigger, it could be smaller, but it's just not true. That's a two-tailed test. All right. So let's look practically. How do we do this? How do we actually calculate, how do we actually do a hypothesis test? So step one, we calculate our t-statistic. All right, we use our sample mean minus the mean based on the null hypothesis divided by the standard error. All right. Step two, we choose a level of significance. We choose an alpha. We choose the probability of type 1 error that we're willing to accept. Normally, this will be, actually exclusively what this will be in our actual analysis is alpha will be either 0.1, 0.05, or 0.01. All right, I'll show that more later. Okay, step three is we look up our p-value on a t-table. So how do we read a t-table? These are the steps. I'll show you what a t-table looks like in just a moment and run an example. Reading a t-table. First, we find the row corresponding to our degrees of freedom. Degrees of freedom are our sample size minus 1. We compare our t-statistic to the t-statistic values across the row. We find the largest value in the row that is still smaller than your t-statistic value. We find the p-value that corresponds to that column. And if our p-value is smaller than or equal to our chosen alpha, we reject the null. All right, those are the steps. I'll illustrate it. All right, we will read our t-table in the next slide. Assume that we have calculated a t-statistic of 1.9 and we have a sample of 15. All right, so our t-statistic is 1.9 and our sample size is n equals 15. So let's do it. If our sample size is 15, then our degrees of freedom is 14. So here's our t-table. This is what it looks like. Take a second to digest this. All right. The first thing we do is we go to our degrees of freedom. We said our degrees of freedom are 14. All right. We follow 14 across. Let's go up. We find our row. We did that. Okay. Compare our t-statistic to the t-statistics values across the row. All right. Find the largest value in the row that is still smaller than your t-statistic. All right, so we said 1.9. All right, so let's go across the row. Smaller, 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 bigger. Okay, then here we go. We find the value that is still smaller than ours, the largest value that's still smaller. All right, then what's the next step? Find the p-value that corresponds to that column. All right. So we come across here. Here's our value. What we do is we take this up to the top. And these are our p-values. Okay, these are our p-values. We have a p-value for a one-tailed test if we're doing a one-tailed test. And we have a p-value for a two-tailed test if we're doing a two-tailed test. Let's see. I lost track of where we are. Here we are. So there's a one-tailed test, two-tailed test. So let's assume we're doing a two-tailed test. That will be pretty common. We do a two-tailed test. That means this is our p-value. We have a p-value of 0.1. We have a p-value of 0.1. Okay, so that means that there's a 10% chance of finding a t-statistic. Really what this means is that there's a 10% chance of finding a t-statistic that is greater than this. And so we know that there's less than 10% chance of finding a t-statistic at least as large as the one that we found as 1.9. All right, so then, we needed to choose a significance level. We didn't do that. Let's choose a significance level of 0.1. That means we're willing to accept 10% chance of type 1 error. That means if we're here, okay, we go up here, we find 0.10. This 0.10, or 0.1, 10%, our p-value is as big, it's equal to our significance level, our alpha, which means we reject the null. So we will reject the null. in this hypothetical example. All right. We will do this in class, so brush up on this, review this, and be ready to do it in class, and of course I'll be there to help. All right, now I just want to take a quick moment to discuss another issue here before I move on to the next final topic. Okay, I've mentioned type 1 error and type 2 error. I want to illustrate the fact that we're always going to have type 1 and type 2 error. We're always going to have some amount of type 1 and always some amount of type 2 error. And actually, if we want less type 1 error, we have to accept more type 2 error. And if we want less type 2 error, we have to accept more type 1 error. Okay, so these things they trade off with each other. Let me illustrate that here. So here we've got two distributions. We've got a sampling distribution of the mean if the null hypothesis is true. And we've got a sampling distribution of the mean if the alternative hypothesis is true. Okay? Now, anytime we have a particular mean, so let's say some critical value of the mean, the chances of committing type 1 error is the space below the function for the null hypothesis and to the right of that value. This is the type 1 error. So I illustrated that before. But what I haven't illustrated yet is the probability of committing a type 2 error. The type 2 error is this blue space. So let me explain here. So what are we saying? We're saying that if we find a mean that is so unlikely, that it's so unlikely to occur if the null hypothesis is true, that we would reject the null hypothesis. That means if we find a value that's out here, we will reject the null hypothesis. If we find a value that is above this line here, this critical value, this is any mean, so some critical value here. If we find a value that's above this, then we will reject the null hypothesis. The probability of doing that, if the null hypothesis is true, is this space here shaded in red. Okay. Now, if we wanted to reduce the type 1 error, we would set our critical value farther to the right. And that would reduce the probability of committing a type 1 error. Okay. But now, what is the probability of committing a type 2 error? Now remember, a type 2 error is when we fail to reject the null when in fact the null is true. I'm sorry. It's when we fail to reject the null when in fact the null is false or the alternative hypothesis is true. So let's think about that. In this example, if we find a mean value that's to the left of this cutoff, we will fail to reject the null. We will say that we have evidence to suggest that the null is true. We will fail to reject the null. But if the alternative hypothesis is true and the null hypothesis is false, we will be committing a type 2 error. Well, what's the probability of committing that type 2 error? That is the space underneath the distribution for the alternative hypothesis and to the left of the cutoff. So that's this blue space here. This blue space here is the probability of committing a type 2 error. This is, I've failed to reject the null, but the null is actually false and the alternative hypothesis is true. And so this is the probability of committing a type 2 error. Now you can see that you can affect the probability of type 1 and type 2 error by where you set your critical value. If you want very little type 1 error, then you will say you'll pick an alpha of 0.01 and you'll choose a critical value that's way out here. You'll pick a critical value that's way out here. But if you did that, if you picked, I'm even going to add this. I'm going to add this to the slide. I'm going to add it right now. If you picked a critical value way out here, then this would be your type 1 error. This would be your type 1 error, this red space. And then you would have type 2 error. I'm just going to fill this. This is having live action. Boom. your type 2 error is going to be this space here. Obviously, this isn't perfect. So excuse me for it not being perfect. Okay. All right. All right, this is going to be good enough. All right. So if we picked a critical value that was way out here, there would be very little type 1 error, but that also means a big increase in the type 2 error. It's a big increase in the type 2 error. Okay, I'm going to add a slide with this on it. That way it's not so cluttered here. And so when you're reading this at home on the slides. Okay. So if we move this over, you know what, I'm going to add an animation too to make this even more clear. All right, I'm going to add that. Let's do this. All right. So if we move our critical value over here, now this is our new critical value. In that case, the probability of our type 2 error has gone up and the probability of our type 1 error has gone down. Let's put this into some intuition. If we say we really don't want to commit a type 1 error, that means we really don't want to conclude that fertilizer helps farmers when in fact it doesn't. If we say that, then we say, well, man, I need a lot of evidence before I'm willing to say. I need a lot of evidence before I am willing to say that fertilizer helps farmers. In that case, there's a very small chance of type 1 error. That means you're going to set your alpha to like 0.01 and you have very small chance of type 1 error. But if you set yourself at such a high significance level, then that would imply that there's a really high chance of committing a type 2 error. It's much more likely for you to fail to reject the null hypothesis when in fact the null hypothesis is false. So if you say, I need a lot of evidence before I'm willing to say that fertilizer helps farmers, you might not get that evidence. And you might conclude that fertilizer doesn't help farmers when in fact it does. And if you do that, then you will be concluding that you shouldn't give fertilizer to farmers, and that actually hurts the farmers because now they're not getting the help that they need. Okay, so that's the trade-off between type 1 and type 2 error. All right, now this is the last thing I want to do in the slides, and then we're going to move this over into the Stata tutorial. Hypothesis testing on 2 means. So this would be a case where we want to look at, okay, let's just read this. We might want to know whether 2 variables or the sample variable for 2 groups of people are significantly different from one another. This is going to be very important for us. We're going to do this. We're going to do this in just a minute when I move over to Stata. So for example, imagine we want to know if individuals that finished high school have greater incomes than individuals who have not finished high school. That means we want to know if the expected income for those who have finished high school minus the expected income for those who have not finished high school is greater than 0. We would answer this using a t-test that compares 2 means. Okay, so let's see what that looks like. So our null hypothesis is that there is no difference in the means. There's no difference between the 2 means. There's no difference in income between people that have finished high school and people that don't. All right, that's our null. That means there's no difference. All right, our null hypothesis is that the average income for people that have finished high school minus the average income for people that haven't finished high school equals 0. That's our null hypothesis. Our alternative hypothesis in this case is that there is a difference. Okay, I want to change the language in the slide. In this case, the alternative hypothesis is that there is a difference. All right, this would mean that the average income for people with a high school education minus the average income for people without a high school education is not 0. All right. The null hypothesis is not true. All right? And the way that we do that We test it using the t-test, test it using a t-statistic, just like we did before. But our t-statistic is here, where what we have is we have the difference. We have the average income for people that finish high school minus the average income for people that did not finish high school. Actually, I need to make this more clear, so I'm going to exit here. Minus our null hypothesis, right? Our null hypothesis. Minus our null hypothesis. Okay. Minus our null hypothesis. All right. So this is our t-statistic. But, all right, so I wasn't totally wrong, but I just want to illustrate this. But we know that our null hypothesis okay, I don't know why this is a different size. It's not, all right, so I'm just going to illustrate this live here. All right. We know, so here we go. This is our null hypothesis. So we take the difference between the difference in means minus our null hypothesis divided by the standard error of the mean difference. All right, that's up here. I'm going to show that in just a second. But we know that our null hypothesis is that this difference, the difference between the means, is actually 0. So we can just delete it. It's not actually there. All right, that's why I had this here in the beginning, but now I've illustrated it. Okay. All right, so it's the difference in the means divided by the standard error of the mean difference. All right, this is the standard error of the mean difference. It's the sample variance for the sample income variance for those that have a high school degree divided by the number of people in the sample that have a high school degree plus the sample variance for individuals that don't have a high school degree divided by the number of people that don't have a high school degree. All right, and it's the square root of that. This is the standard error of our mean difference. And so we use these two things to calculate our t-statistic, and then again, we use our t-table to determine whether or not, to determine our p-value, which will determine whether or not we have found a statistically significant, to determine whether or not we reject the null hypothesis. If we reject the null hypothesis, then we would say that there is a statistically significant difference between these two means. We would say that there's a statistically significant difference between the expected income for individuals who have finished high school minus the expected income for individuals that have not finished high school. All right, let's practice this in Stata. All right, we're going to practice this in Stata. We're going to use the same data set we mentioned before. This is the data set that has data on hourly wages, education, and experience. And we're going to ask ourselves two questions in this Stata practice. The first question is, do individuals that have a high school education or more have higher wages than individuals that have less than a high school education? We're going to ask ourselves that question. We're going to use some hypothesis testing. All right. Next question is, do individuals that are employed in manufacturing have higher wages than those that are employed in other sectors? All right. These are the two questions we're going to ask. So let's open up Stata. We already opened up Stata before, so let's go back in and let's begin the process. All right. So let's write down 2 research questions. All right. Question number 1. Basically say this: do individuals with a high school degree have higher incomes? All right. And then question number 2, we'll put this down here. We'll answer them separately. Question number 2 2 is, do individuals that have that work in manufacturing have higher incomes? Actually, I should say wages because we're looking at wages in this data set. Okay, wages. All right, so 2 research questions. Let's take them in turn. I want to know, do individuals with a high school degree have higher wages? Well, how do we ask that question? How do we answer that? Using our data, using the tools that we've worked with so far. Well, first, I'm going to be really interested, well, what kind of data do we have on education? Do we have data that tells us whether or not individuals have a high school degree or not? Let's see. I'm going to use tab, and I'm going to do tab EDUC. Use tab EDUC to see what are all the different values of my education variable. So I look in here, and okay, we've got some individuals here. So no education is measured in years. So 0 years of education, 2, 3, 4, 5. Okay, now let's think about this. Individuals that have 12 years of education or more, 12 years of education or more, are the ones with a high school degree. Individuals with 11 years of education or less are the ones without a high school degree. All right, so then I'm going to create a variable that's going to tell me whether or not someone has a high school degree or not. I'm going to create a variable. I'm going to call it HS, high school. I'm just going to say HSD, high school degree. All right. I want that variable to equal 1 if EDUC is greater than or equal to 12. And then I want HSD to equal 0 if they have less than 12 years. So then I'm going to use this command, replace HSD equals 0 if EDUC is less than 12. All right. And then I want to label that variable, label variable HSD equals 1 if high school degree equals 0 if not. All right, that's just the label, just so I know what it is, know what it means. I'm gonna highlight these. You know what? I'm even gonna give some more notes here. Generating a variable that generating what kind of variable? A binary variable that equals 1 if they have a high school degree. All right, that's what I'm going to do. All right, so then let's highlight this and hit it. Boom, generated the variable. We can even open up our data set and take a look. HSD, all right, our brand new variable. We can look at our label over here. Okay, look, great. Equals 1 if they have a high school degree, equals 0 if not. Excellent. So here's our variable. This person doesn't have a high school degree. This person does. This person doesn't. This person doesn't. This person does. Okay, this is great. We've got our variable. Excellent. Now I want to try to answer the question. Let's try to answer the question. First, before we try to answer the question using our hypothesis testing, let's just see if there's a mean difference. So we did this in the last assignment, but let's do it again. Is there a mean difference? All right, so let's do it. Let's do mean wages if HSD equals 1. So this would be the mean wage for people with a high school degree. All right. And then we'll also do the mean wage for people without a high school degree. Mean wages it's just wage, isn't it? There we go. Wage if high school degree equals 0. All right, so then I'm going to highlight these two, and it's going to run. Let's see. What do we get? What do we get? All right, here we go. Here they are. This is the mean wage if high school degree equals 1. This is the average wage for people if they have a high school degree, $6.4 an hour. Here is the average wage if they don't have a high school degree. All right, average wage if HSD equals 0, $4.06 or $4.1 an hour. So if I look at this, and I just want to calculate, let's just get my calculator out. If I look at the mean difference, here's my calculator. I had 6.4 minus 4.1, 2.3. 2.3. So that's a big difference. $2.3 an hour. We could say, all right, people with a high school degree make more income from people that don't. And from the first lecture, that was fine to say that. But now we know better. Now after we've done hypothesis testing, we know better. Now we know that that mean difference might not. Difference in the means at 2.3. That might not mean that in the population there actually is a difference. That 2.3 difference could just be by chance. We need to do a hypothesis test. We need to do a hypothesis test to see whether or not that's significant. So we have a mean difference of around 2.3. But is it significant? Is it significant? By significant, what do we mean? I'm typing the notes as we go so you can see this later. A significant difference means that we reject the null hypothesis that there is no difference. We could say it another way. This is another way we could say it. Also, we could say a significant difference means that we find evidence that there really is a difference in wages between people with a high school degree and people without a high school degree. All right. So to do this, we need to do a hypothesis test. Okay. I'm typing this out just so that you have some extra notes. I like to have notes in my do files so I keep track of what it is that I'm doing. Sometimes I have do files that have more notes than code. All right, so hypothesis test. What's our hypothesis? Our null hypothesis is that the mean for people with a high school degree minus the mean for people without a high school degree is equal to 0. That means there's no difference. That's our null. Our alternative hypothesis will be that x minus y, so the people with high school degree minus the wages for people without a high school degree is greater than 0, or it is less than 0. All right, that is what our hypothesis test is going to be. How do we do this? This is a mean difference t-test, just like we did in the lecture, just like we had right at the end of the lecture. Right at the end of the lecture, we did the mean difference. So now I've just written out my null and alternative hypotheses. Oh, hey, look. This should be This should be A, alternative. All right. All right. So I've written out my hypotheses. Now I'm going to do the test. But of course, once we're in Stata, we don't have to look up t-tables or anything like that. We actually do something pretty straightforward. And this is a really, really helpful code. So let's learn this one. What we're going to do is called a t-test. That's it. Very, very simple. T-test, wage, comma, by HSD. What this does, what this very nice line of code does, is what this will do is it will generate the average wage for people with high school degree, the average wage for people without the high school degree, the difference, and then it will show you whether or not that difference is statistically significant. It reports the p-value. So let's run it. So here we go. We're doing our t-test. Here is our output. Here is our output from our t-test. There's a lot of information here. Let's go through it. Okay, so this column here says group. That means this is the different values of the HSD variable. 0. This is when HSD equals 0. That means when they don't have a high school degree. 1. This is when HSD equals 1. That means that they do have a high school degree. All right. Then we have observations. Observations, the number of individuals in the data set that fall into either category. Basically, we have 116 people without high school degrees and 410 people with high school degrees. Then the mean. Now we have the mean, the average. We have the average wages for people that do not have a high school degree. That's what this would be. Okay, the standard error, standard deviation, etc. All right, this is the mean. This is the same as we see up here. So this nice line of code generates the same thing that we had up here. We didn't have to run the mean command separately. We could just run the t-test and it'll give us the mean. Okay, now here, this is the mean for the people that do have the high school degree. So the mean for the people that do have the high school degree is 6.4, just like we saw above. The mean for the people without a high school degree is 4.06, 4.1, just as we found before. Okay, now it also gives you the difference. All right, that it reports that down here. So down here it says diff, that means the difference. So here's the difference. They take the mean for people with a high school degree, they take the mean for people without a high school degree and subtract the people with a high school degree, and they get the difference. In this case, it's negative. All right, so here is the mean for people without a high school degree, a mean for people with a high school degree, and then the difference between them. And finally, we'll come down here and we'll find our p-value. We'll find our p-value. Now remember, our p-value gives us the probability of finding a t-statistic greater than or equal to the t-statistic that we find. Now this table, let me back up. This table also gives us our t-statistic. It's down here. T equals this. This is our t-statistic. Our t-statistic measures the number of standard deviations away from the mean if the null hypothesis is true. This t-statistic is huge. Remember we said that if a t-statistic is larger than 3, then it's a really extreme value? Well, a t-statistic is, of -6 is enormous. So this thing is definitely statistically significant. We are definitely rejecting the null hypothesis on this one. We find the probability of finding such a high t-statistic down here. This probability that t is greater than t, this is our p-value, and it equals 0.0000. That is a tiny p-value. That means that we will reject the null hypothesis. And we're going to reject that null hypothesis at the 1% level because this p-value is smaller than 0.01. Smaller than 0.01, then we reject the null hypothesis at a 1% level. All right, so then we've done it. We've done our difference. We calculated our differences, and now we went back and we looked, okay, is it statistically significant? Yes. Yes, it is statistically significant. So we can come back over here and just make a note of it. We can make a note of it. Yes, there is a statistically significant difference between the wages for people with a high school degree and people without a high school degree. All right. This would mean we reject the null hypothesis. We reject the null hypothesis. We have provided evidence that wages are higher with a high school degree. Now, if I asked you, is this causal? Is this causal? What would you say? We found this statistically significant. That means that it is. That means we have strong evidence to suggest that wages really are larger for people with a high school degree than people without it. Does this mean it's causal? Does this mean that high school degree causes you to have higher income or higher wages? Is this causal? The answer is no. Statistical significance helps you to determine true correlation, but on its own, it does not tell you anything about causation. All right, let's go. Let's keep going. Let's do question number 2. Question number 2, I'm going to give this 2 stars, make sure it's a nicely separated out category here. All right. Question, I'm going to add 2 stars here. I like keep things nice and neat. All right, question number 2. Do individuals that work in manufacturing have higher wages? Do individuals that work in manufacturing have higher wages? Well, let's open up our data just to get an idea for this. So we've got wage data. Okay, we've got this job variable. And this job variable is clearly it's categorical. It's just different categories. We'd also call it a string variable. That means it's composed of words, not of numbers. Okay. Well, gosh, how do we figure out whether or not wages are higher for people that are in manufacturing than people that are not? Well, what we first want to do is we're going to generate a binary variable that indicates if a person works in manufacturing. All right. To do that, let's do gen. That means generate, gen. What are we going to call this? We're going to call it manu. Not like Manchester United. Manu is in manufacturing. All right, generate manu. This is going to be a dummy variable. And we want this binary variable to equal 1. We want it to equal 1 if that job variable equals manufacturing, and we want it to equal 0 if it equals anything else. All right, so this is how we're going to do it. This is kind of tricky. If job equals manufacturing, you have to make sure you spell it right. And you want to make sure you get the syntax right on this code. What this is doing is I'm generating a dummy variable. It will equal 1 if job equals manufacturing, and it will equal 0 if it doesn't equal manufacturing. You have to get the spelling right. All right, you have to get the spelling right on string variables. Let's do it. Boom. Did I get it? I got it. All right, let's take a look. Actually, real quick first, let's give it a label. This is really good practice to get into of labeling your variables when you create it. All right, label variable manu equals 1 if person works in manufacturing. Manufacturing equals 0 if not. Excellent. All right, let's give that a label. Boom. All right, let's take a look at our data, see what it looks like. There it is. There's our manufacturing, our new manufacturing dummy variable. Look at it. All right, if job equals manufacturing, manu equals 1. Let's see. If job equals manufacturing, manu equals 1. If job equals manufacturing, manu equals 1. All right, there we go. So now let's do it. Now, if I wanted to know, I could go through all the same steps that I did up here. Calculate the mean, subtract, find the difference. We don't need to do that. Now that we've learned this t-test variable, we're going to go straight to that. Straight to the t-test. T-test for mean difference between people that work in manufacturing and people that don't. All right, so let's just do it. T-test. T-test wage, comma, by manu. All right, what's this going to do? It's going to calculate the mean for wages for people that work in manufacturing, the mean of wages for people that don't work in manufacturing, the difference in the means, the t-statistic, and the p-value. All right, let's do it. There it is. Same result table, just like before. We've got the mean for people that don't work in manufacturing. We've got the mean for people that do work in manufacturing. We find that there is a difference. The difference is 0.04, basically. So people that work in manufacturing make basically 4 cents more. But our t-statistic is minus 0.09. That's a very small t-statistic. That's less than 1 standard deviation away from the mean. And so we come down here, we look at our p-value, and what do we find? It's 0.926. It's a very large p-value. There's a 93% chance of finding a t-statistic at least as large as the one we find. So we fail to reject that null hypothesis. We only reject the null hypothesis if that p-value is smaller than our significance level. And our significance levels are usually 0.1, 0.05, or 0.01. And this one is way bigger than 0.1. And so we fail to reject. We fail to reject the null hypothesis. So let's make a note of that. We fail to reject the null. We conclude that we do not have evidence to suggest that people that work in manufacturing have higher wages. Okay, so there we go. That's how we do it. This is a super valuable technique in practice. It's a super valuable technique in practice. All right, I'm going to save this. I'm going to save this in our do files lecture number 2. I'll post this online, lecture number 2. Statistical significance. All right, and there we go. Now the last thing that I want to do, the last thing here, I know it's been a long lecture. All right. So I just want to show you what it looks like to put this in a professionally formatted table. So here we go. Actually, I'm going to change this live action. All right, I'm going to fill in this table. This is what a nice table looks like. Table 1, and then you have the title of the table, and the title makes sense. This is a professionally formatted table for reporting mean differences. So this is wages for high school degree. All right, what's our mean for the people that have a high school degree? It is 6.4. 6.4. All right, this one's going to be wages for no high school degree. And what was that? What was that? That was 4.1 basically. So we'll put that here. 4.1. What was the difference? 2.4 basically. All right, 2.4. That's the difference. All right, and then I report whether or not it's statistically significant by putting some stars on it. The number of stars indicates how statistically significant. It indicates at what level of statistical significance that I'm using. So basically, if my p-value is smaller than 0.1, I'll use 1 star. If it's smaller than 0.05, I'll use 2 stars. And if it's smaller than 0.01, I'll use 3 stars. If we go back to our p-value was smaller than 0.01, so I use 3 stars. That means this is highly significant. That means it's very unlikely. Very, very, very small chance of type 1 error. Very small chance of type 1 error. That means that we really do think that we are observing a true difference in the population. Okay, thank you very much, everyone. Hope you appreciated the lecture. Take careful notes, write down your questions, and I can't wait to see you in class. Thank you, and have a great rest of your day.